So welcome to today's Ascendo Reliability webinar. We're going to talk about hypothesis testing, some of the basics, some of the things that we probably should know if you're going to use this tool, and some things you should be aware of, especially if you're going to use this tool or this method. I'm Fred Schenkelberg, and I'm continuing my fundamental series of stuff, kind of thinking through the underlying assumptions and backings and pinnings and when and why to use a particular method or tool and things to keep in mind as you use it. Mostly because my goal here is to connect these webinars to pages that, for example, we'll talk about hypothesis testing and include what it is and articles and tutorials on how to do it and what kind of things to work on and not work on, where it works and doesn't work, and so on. Because we've got a lot of content on the site on hypothesis testing and a lot of the other things that we do on a day in and day out basis. And so we're looking at making pages that help people get up to speed with these various methods and tools and give them a kind of an ad hoc course, the lack of a better term for it, or learning guide, I guess, or something like that. So these webinars I'm trying to get, besides the podcast that comes out of it and the recordings, which seems to be very popular given the traffic they're getting, we also want to make it so that if you really want to dive deep into a particular topic, that we're going to try to organize some material such that makes it a lot easier. So let me dive into this and hopefully everything keeps working. Let's see. Now, when we make a measurement, we have one point of data, or we make an observation, whatever you want to call it. We have one thing, and we might know the width of this leaf or the height of it or its color or whatever it is of interest for us, yet that's all we know. And it takes having a second point to make a comparison, to judge whether that was a really, really big leaf or a particular color we liked or something else. But is it, we often make measurements, not just to admire those measurements, to appreciate the width of it and have it's 2 inches wide. Well, that's great. Yet we often very intuitively start making comparisons. Is this an average size for this leaf? Is it on a larger size? Is it on a smaller size? Is it in spec, for example? Is it different than other trees that are of similar species? Are these typically bigger or smaller? And if we went and got 2 leaves, one from each tree, for example, and compared them, we could do it by observation. We could make measurements and we'd have 2 points of data. And the issue is that every leaf on this tree is different. They're at a fundamental level, they consist of a different number of atoms. And if we could measure it fine enough, we would determine that they are fundamentally different in so many ways. Growing up, I lived in an area that got regular snow in the winter, and somebody told me that no two snowflakes are the same. So I spent the whole winter one year, catching snowflakes when they were coming down by themselves and trying to find I'm drawing a blank on the right word, but trying to find something that would refute that claim that they're all different. I was of the opinion that there's so many flakes coming down and there's so many opportunities for them the same. If I measured long enough, I would find 2 that are identical. Well, that didn't work out. I got too cold and went back inside. When we really want to know if there's a difference, or we have the opportunity, like most of us do, is to make lots of measurements on so many different things that are important to our business and to our processes and to our systems, we tend to get a lot of points. Now, the individual elements that we're measuring, we can detect all kinds of differences. It's when we take a look at them in a little more refined way, is that we start to understand that some of the difference matter, and some of the differences are vague or fuzzy. We just really can't tell if it's really different or not. And sometimes it's obvious that they're the same. They come from the same group or same cluster or whatever the right term is. The idea is that we make measurements and observations with our processes and products and systems and with our vendors and so on, even with our customers, customer satisfaction surveys and so on, in order to detect changes or differences. And so hypothesis testing is one of those tools that is one of the ways that we can check on those differences to see if they're real or not. So let me pause there with that vague description of hypothesis testing. And how do you use it? Do you use it? What kind of work do you do with hypothesis testing, if at all? I'm really curious if this is a popular approach to making comparisons, or do people use something else? See if I got any comments here. Let me, no, there we go. Never used it. I may end up talking you out of using it and try a different method. We'll talk about that later. Not in practice any. So sample of two, we got, no, we're not using it. You either haven't used it or don't use it. Well, I may end up confirming that's a good move. Contour plots in two populations. Interesting. Good, good. Those are two. So 3 points of no, four really say no, I'd rather use. Okay, that's encouraging. Makes me wonder why he spent so much time learning this way back when, but we'll get into it a little bit. So the basic idea is it's a way to determine if there's sufficient evidence to support a hypothesis, hence the name hypothesis testing. And what we do is we take a sample from the population. If we had measured the entire population, we would have, essentially complete data, and we wouldn't need to, we would know whether it's changed or not. The mean would be the mean if we made a measurement of the entire population. And if it's in the direction that is of interest to us and enough of a difference that it's significant in that it's practically significant, we could say that, yeah, we know it's changed, right? That comes with measuring the entire population, though. And we rarely have that opportunity. Now, some processes do 100% inspection and measurements and so on. Yet, when we're measuring it for 1 week's production, if the population is every widget that we've made, well, we're taking a sample at that point. Or we're in development, we're making prototypes or early production runs, and we're trying to learn something about what the entire population of future production is going to be. Again, that's a sample, and there's murkiness or uncertainty that's involved in that. Yet we do need to answer questions. Is this product meeting specification, or is it if we're doing failure analysis, does this remedy that we're invoking, does it really solve the problem? And does it do it, for a variety of different reasons, but does the root cause of the problem not happen? And how do we know? Let's measure enough samples to detect whether that's occurring or not. And oftentimes it's just, is it different? We have lots of tools that help us determine if there is a difference or not. And we'll talk about some of those a bit later. The idea, though, is it's one tool to make a comparison. And it really only works, from what I've seen and understand, is between two things. So a sample and a specification or a limit of some sort, or two samples that we're comparing to each other. As soon as we start doing 3 samples or 4 samples, then analysis or ANOVA and DOE And there's some non-parametric methods that allow us to compare three things. Unwittingly, years and years ago, I made that mistake. I had three samples, three different production lines, and I'm trying to compare them. And I compared A to B and A to C and B to C. And thought I was doing a good job. All of them were at 90% confidence, all this other happy stuff. And then I realized, if I work this out, I really am not getting the answer I'm thinking I'm getting. And so I thought, well, there's got to be a better way. And that got me into lots of other methods. So compare two things is usually the element of it. And it's usually to determine some effect of a change or a process or comparing it to a specification is where I've used it before. I'm sure there's other applications for it. The other thing is that it can compare a whole range of different parameters. Comparing the means of two samples is a common technique, yet we may be more interested in the variance, the standard deviation element of that. Is our process change reduce the variability? And that's often a very good thing to do. And there's specific tests that allow us to do that. And it'll compare all kinds of different things if you're creative enough and have enough interest in finding the way to do it. Now, one of the reasons we do this is that everything we deal with, everything we measure is random. It has some element of randomness to it. No two leaves off a tree, or no two, allegedly, hypothesis would be, is that no two snowflakes are the same. And it's right out of, in my mind, it's right out of the statistical, or what is it called? The scientific method. We make an observation. Is that to be expected, or is that different? So if I turn the heat up, the reaction of this chemical process will increase. Well, Arrhenius noticed that and kind of wrote down an equation for it, basically, that described that relationship. Yet he also figured out, and this is where a lot of times when we talk about accelerated life testing that we get in trouble, is that the actual activation energy, and anybody that's used the Arrhenius equation knows what I'm talking about, is very tied to that specific chemical process. And if it's off a little bit, if we assume it when we shouldn't be doing that, or we don't have the right activation energy, we'll get a different answer. And even within, I'm thinking of an early test I did. It was with polymer. And it's very different than solder, which is what's called eutectic. So if you heat a solder paste up to a certain temperature, a particular temperature, it will melt pretty much all at once. It's just the term I've heard associated with that is eutectic. Or polymers, if you start melting them or heat them up, is because of the differences in chain lengths, is some of it starts to melt or soften much below its stated melting point. And later, it'll get, as you get closer and closer to its rated melting point, or where it's going to melt, it starts to soften and get rather gooey, and then eventually it's all melted. But it's because of the differences in lengths of chains that are within that body of polymer. We understand a good number, or a pretty good number of ways randomness happens. And some of them we pay attention to and measure and account for. And other ones we just understand that it's going to be different. The issue is that the randomness is there, whether we like it or not. If we assume that we have very, very small variation and that we only need a very small sample size, we may or may not be making a good assumption there. It's because the world doesn't care what our assumption is. It's going to be what it is. Now, years ago, I was working with a team in South Korea that it was an electronic component of some sort. And we were talking about hypothesis tests and how do you calculate sample sizes for it and so on. And they wanted to know a very tight tolerance with like a 99% confidence. And I thought, in all my experiences, anything like that, you would need thousands of samples. Well, it turns out that their standard deviation or their variance of their process was incredibly small. They had worked to not just get into the specification, but to, because of their techniques and the methods of making their products and so on, is the actual variability from one component to the next was very, very small compared to the specification they were dealing with. And they were, if you were using a Six Sigma or a CPK kind of value, it would be in the 20s or 30s. It would be, they were so far away and so small of a variation that it was near impossible, given that they also had a very stable process, that a product would be out of the specification for one of the values that was important to them, which is great for them. Their products were actually pretty decent and were very consistent in all kinds of ways you can measure it. In that case, we calculated the needed sample size to determine if something is out of spec, say a weekly batch or a daily production, was less than one sample. And I've never run into that since or before that occasion. So it can happen that you could use very small samples, but it also requires that you have a very stable process and a very consistent process. And so part of this randomness that we deal with comes in many different forms, but in one place, it's what's a sample? What is the concept of a random sample? And I'll use an example of height, which I think the we can all relate to or at one point or another, is that if I'm living in an area that has people that are generally adults or generally very tall, like parts of Northern Europe are that way, and there's other groups of people around the world that tend to be rather tall compared to the population of all humans that are alive today. So if I happen to be in that city where there's lots of tall people and I do a random sample by, you know, asking people to be measured or measure people as they're coming through a hallway at some venue or something like that, or my sample is going to tell me about people in that group, in that city, in that region of the world, or in that cohort. If I'm interested in the height of people all over the world, well, my random sample is pretty narrow, right? It's not all that random. It's random in the people I can touch and meet in that city. So my sample is going to inform me about that city, about the areas I actually pull samples from. And in production facilities or in and building a product and doing prototypes, we often run into almost exactly the same problem, right? We have the desire to make conclusions about the eventual, all the products that we're making. Yet we've only made a couple hundred. And it's the first time the production's coming up, and we're still possibly making process changes and design changes. Is that a fair sample of our production, or when we ramp and make thousands of these units? Yet what I run into is, in the practical sense, it's really the only thing we've got available to work with. So then we use it, right? We understand that there's a not total random sample here. It's not from the population we're trying to make an estimate about or understand. And sometimes we have to deal with that and recognize that it might be biased. It might be off from what we really need. The other place I see it is when somebody's on a production line and they sample the one on the edge of the pallet or the ones they can reach, or they measure it once an hour. And the once an hour one, I said, well, what happens if we measure it 5 minutes from now or 20 minutes from now? Well, what if we measure it, on a random time frame rather than a fixed time frame? What would happen? And the technician I was working with, she said, well, we tried that once and we got really bad answers. What do you mean bad? She says, well, they were out of spec most of the time. Well, why do you measure it right on the hour? Well, and it turns out, to make a long story short, is that the production operators knew that their inspection was on the hour. So about 15 to 20 minutes prior to that, they would make a measurement and they would adjust the process. And it was a continuous process, and the getting the blend just right or getting the mix just right were things and temperatures involved with the process could be controlled. Yet they knew that the only time they really need to pay attention to it was just before the inspection occurred. And then it would get dialed in, and then normal randomness of our process and of the mix of materials and so on would drive it off to wherever it was going to go. Sometimes not in specifications, and sometimes it would be okay. And yet the inspection process created the bias. And because it wasn't random in the sense of alerting the operators to when the inspection was coming on, and they were chastised if their process was out of control, out of spec. So they learned that real quick and said, well, the only time we really need to pay attention to it, because it was difficult to bring the process into control, and there was a lot of work done to improve that ability and reduce variation. Yet they knew that they only got measured once. And so and I'm really wondering about how randomly I spelled plenty, but I'll have to look that up later. But the underlying idea of why hypothesis testing works in the way it works is that we do have a random sample, and it's sampling something that we're trying to make a judgment about. So if it's a population of humans around the world, it might be very difficult to get a truly random sample from people from around the world. But sometimes that's not what we really need to know. We want to know if our prototype is in specification. Was our prototype going to last long enough? So we take a sample from the prototypes that we have and make that judgment that's a fair sampling of that population, which we defined as the prototypes. So being very careful about how do you extrapolate the results of your sample out. And it doesn't apply just to hypothesis testing. It's something we probably should do a webinar on. But there's a third kind of randomness. Anybody know what that one is that I haven't mentioned yet? Yeah, Carl, you read my mind. I've got a map basically that illustrates a whole slew of different types of hypothesis testing, but not all of them by any means. Right. I don't see an answer on the other kind of randomness that we need to be concerned of. We'll get into it a little bit later. All right. What we're mostly compared in is making a comparison of two things. Talked about that a little bit, right? And so we take a sample, we make some measurements, and we can compare it to a specification. And another one is we can take two samples, say from line A and line B. Are they doing the same thing? And we can do it before and after a design change. So if we're notice some issue or problem in our root cause analysis of a recent failure, wherever it occurs in our life cycle, and we decide to make a design change or a vendor change or a process change, one of the steps that we need to be aware of is that, well, did it really change it? And so if we had 14 defects per 10,000 feet prior, and we changed the extrusion process to reduce the source of those defects, we could run another 10,000 feet or a couple more batches of this stuff and monitor how many defects per 10,000 feet we got. And then we could make a judgment. Did it create more defects or different kinds of defects, which was something we were worried about? Or did it eliminate the cause of the defects that we were getting? And in this particular example, it was unmelted polymer coming through the jacketing a cable, and it would create a bump in it, which had not only cosmetic issues, but thermal issues. So we made a change, and then we monitored it, collected data, and then ran a calculation. And it turned out we didn't really need to make the calculation because it was so obvious. And we'll talk about, all kinds of ways to, other than a hypothesis testing briefly, about how to detect those changes. But it comes in handy for all kinds of stuff. And so Carl asked one or made one comment about all the different types of them out there. And it, from that first survey, it didn't sound like very many people were using hypothesis testing. So I guess this question will be rather mute. All right, basic process. I'll go through this pretty quickly. The idea is, let's say we're making a bicycle and we have a frame, and if you're a road bike enthusiast and like, riding your bike in competitions or want to improve your time and doing all these other things, and if you're like me, you just like going fast on a bicycle, the weight of the bicycle matters. So if you have a big, heavy beach strider thing that's a bunch of steel and it weighs 15, 20 pounds, that's an extra set of mass that you also have to get moving. So the bicycle riders, they worry about every gram on their bicycle, and the frame is just one part of it. So let's say we do a process change, and will this process change reduce the weight of the frame? Well, the basic process for hypothesis testing is we set a hypothesis. What is it we're trying to detect? So we wanted to know, if we make this change, will it lower the weight? Will it reduce the weight of the frame? And we want to show that we want to determine with evidence that that's true or not. The null hypothesis is that there's no change. And that is kind of if the process had no effect whatsoever, there would be no change. And so what we're really looking for is evidence to confirm for us or prove to us that the alternate hypothesis is true. The burden of proof is in the hypothesis, the alternate hypothesis is that we have to have sufficient evidence that we can say that it is true in this set of samples in this process that we're using. And so we can set alternate hypothesis is that they actually are the same. If we're comparing two vendors and we want to make sure that they are actually the same, not different, then our alternate hypothesis would be is that they're equal to some amount, or we can say it's greater than or less than. There's three different options for setting this up. That sets the stage for then where we do the calculations in the primary work for this. Now, part of hypothesis testing is not just making measurements, right? It's also taking a look at your data and looking at how you collect the data, how you create the sample, what are you comparing in your sample to which population are you working on? I talked about that a bit earlier. But a very good practice, that it's not true for just hypothesis testing, anytime you get a set of data, is I highly advocate, and I know many other people do, is, well, you should plot it. Do box plots, do histograms, do, whichever kinds of plots and images of the data set you can have that give you an insight is this of what the data actually looks like. How does it feel? What's its shape? And how does it spread out? All those kinds of things help you intuitively, to a large degree, really get a good feel for how well your data is going. And do you have any clerical errors? I was making measurements of things that are all about 3 grams, give or take a little bit. And one of them in my handwritten recording of measurements was 300. And so instead of 3.01, it was 3001 or 01. And I thought, I think that was a clerical error. I forgot a decimal point in that. Yet other times it's harder to tell if it's really an outlier or is it a real data point and so on. In this case, I knew that the scales I were using were really focused on like hundredths of a gram, and it would really not like having 300 grams on it. It would be on a different set of scales for it. So it wasn't really feasible for a 300-gram sample to be in the mix. So made the clerical error correction and moved on. But I caught that in a plot. Looking at a great big row of numbers is usually not all that informative. So I nearly always plot it. Oh, I like Bill's comment there is the null hypothesis is never true. Yeah, you can't prove the null hypothesis with a hypothesis test, is the way I understand it. Is you can say that, let's say I'm comparing two vendors and I want one of them to be, a lighter weight frame. And the null hypothesis is that they're equal. Well, I'm not collecting data or setting up an experiment to prove that they're the same. I'm detecting whether the new one is a lower weight or not. And I can create enough evidence if it is actually a lower weight, and a well-designed test will help me understand that it is actually lower, yet it doesn't prove that they're the same. So I think the way I understand it is the alternate hypothesis is either there's evidence to support it or there's not. It really doesn't talk about the null hypothesis. The other part of this, and I know many of you will understand what a type 1 and type 2 error, right? The bane of sampling is that you can have perfect data that shows that it really is the underlying unknown full population is they're really different. Yet there's a finite probability that the random samples I take to make the comparison will show that they are not different. That's one type of error. The other one is they really are different, yet the random sample we take shows that they're nearly identical. So there's not evidence that we can be convinced by that they're different. So we end up with these type 1, type 2 errors just due to the nature of doing a random sample. We could pick samples that happen to be on the high side or the low side, and that'll skew our conclusions about what's going on. And so we use sample size calculations to figure out, well, how do we minimize the chance of those errors? And that goes back to my comment about if I've got a reasonable amount of variation in the process, I usually need lots and lots of samples. I learned that the estimating the beta of a Weibull distribution is not easy to do from a statistics point of view, and you need lots and lots of samples to have a really close estimate or small intervals of uncertainty around it. So if I run those calculations, and I know that there's lots of variation in estimating that, given all the complexities of say, doing an accelerated test, usually with very few samples, the variance around that estimate of that beta value is going to be pretty big. And if I really want that to be minimized, one calculation I did, I needed a couple tens of thousands of samples to make it work. And I thought, I don't think I'm going to get my boss to approve that. So part of the process is plot the data, right? And it's that data that we end up doing the calculation. We do a test statistic, which then we're going to measure to a critical value. So there's really what's the null hypothesis, what's the alternate hypothesis, what's the test statistic calculation at, what's the critical value, or how do we judge that test statistic to what we're interested in? Yeah, what I see in many of the tutorials online and ways of looking at setting up this process is the set of assumptions that come with doing this kind of work. And the randomness also extends the measurement error. And all too often I see people grab the local most convenient measurement device they have, and then they go start making measurements and wonder why this process change, which scientifically or engineering wise, we think will make a significant difference, a real improvement to, say, the reduction of the weight of this frame. Yet they're using a measurement system that is not able to measure in grams. It can measure to the nearest pound, for example, or or stone. I've never measured anything using the units of stones. But the idea is that the measurement error is is always greater than zero, and it adds to the randomness of the things that we're making measurements of. And so a very good assumption to check is your measurement device and measurement system, your observation system, actually capable of making the measurements in it with minimizing the amount of measurement error it adds to the data set, and can save you a whole lot of time and a whole lot of misses in judgment if you actually check that. And it's the measurement system analysis is not terribly difficult. It does take a little bit of time to get it right. Yet, if you're going to make an important decision based on a comparison or whatever statistical analysis or sampling you're doing, is at least check your measurement systems. And it's not just calibration, it's repeatability and reproducibility are the two bigger ones that I've run into. Yet bias and skewness and all kinds of other things play a factor in just adding to the uncertainty. I mentioned the random sample issue is make sure that you're pulling from the population as best you can. And I know that the further you're away from sampling from the population of interest, the less true, unless you've got a sound engineering reason or a scientific reason that your subset, say from this town, is a representative of the population of around the world, for example. But if you don't have that evidence, then it's a question to be very cautious about. The other part, and I ran into this on occasion, is that a good many times, like if we're doing a z-test or a t-test, or two types of comparing a mean to a specification or comparing two means of distributions, is that it says it's got to be normal or reasonably normal. I saw one book talk about. Now, I've never run the, what if or simulation to say, well, how close to normal does it need to be? The general advice is if it's not normal, then you need to convert your data set to normal, take the log of it or the inverse or whatever, is try to get it more normal. If you've got a large sample set, it tends to minimize that. But the idea is that if you're measuring something that in the process is clipped or segregated, making resistors, for example, the actual process of making a resistor is probably creating resistive value, say 100 ohms is their target, and it'll vary. It'll be plus or minus, say 20, 30% of that value. So it'll go from 70 ohms to 130 ohms. It's not unusual. And it'll most likely, depending on how many samples you measure, it will probably be normally distributed. Yet, in the process of making those resistors, they measure them, every single one, and they say, oh, this one's really close to 100 ohms, so we're going to charge more for those. We'll call those precision resistors. I think that was a marketing term, and they could charge twice as much for those. And the remainders, without the ones that are actually around 100 ohms, plus or minus, say, 1% or 5% or something like that, those are not in that population anymore that I bought on the cheap at 20% tolerance on it. But it doesn't have any that are really close to 100 ohms. So it's not really a normal distribution anymore. It's a piece of a normal distribution, or it's truncated. The ones that are way low and way high now become 120 ohm resistors in a different box. So the tails are truncated. So if your process actually distorts the normalness of what you're trying to measure for whatever reason, well, then it starts to say, how far off does it have to go before I have to do something else and pay attention to that? So those are three things I always check if I'm doing it in pretty much not just hypothesis tests, but with any sample. and especially the measurement error. I've made more money on measurement error improvements than I have on actually, running a comparison type experiment. Basic calculation is very simpler for a T or Z test here. It's really similar to when we do normalizing our data for a standard normal distribution. And we were looking for, well, how far away is our sample from our specification or our other sample? How many standard deviation is it away is the way I think of it, a Z value on a standard normal. And that gives us, say, I think it's 0.05 is one point. If we want to detect if something is going to be lower in weight, we do the lower tail, and we would say our critical region or the critical value is based on our confidence or our what we are expecting to say is this is significantly different, statistical difference. One number that always comes to my mind is minus 1.96. There were sort of like magic numbers of 5%, 10%, and stuff like that on the normal distribution lower tail. I think 2.56, I don't remember what it is, but it's right off the standard normal table. And we do a calculation that puts our sample data in that set of terms, and we make a comparison. If it's within that region, then it's not really different. If it's outside that region, it's different. The issue is that the standard deviation of our sample or the variance, the variability of our system really wreaks havoc with this sensitivity or the ability for this to actually detect something that's interesting to us. And that comes into our the next section with issues. Hence the doing the plots, plotting this stuff and charting it or graphing it in various ways to see what's going on with the data. If we notice we have a very large amount of variance, of variability in our data set, intuitively you should know is that detecting a very small change, even if it's an important change that it might be, 2 grams on a bicycle frame, depending on how much money you have, 2 grams would be worth the effort to do. The idea is that if you have a lot of variation in that process, detecting a true change, the unknown true distribution, will be difficult because there's so much noise. Think of it that way. There's so much scatter in the data that it's hard to detect it. So you need lots and lots and lots of samples in order to overcome the ability to detect a minute change. If I'm really interested only in, say, 1,000 gram or a whole kilogram of change, then, well, it'd be a lot easier. If it really is a whole kilogram away, but our variation is on the individual gram size, then detecting that change won't need very many samples at all. You might just pick up the bike and go, yeah, this is lighter. A whole kilogram would make a difference in how much your bike feels just by picking it up. You don't need a real sensitive gauge for that. Unfortunately, we don't tend to work in those great big huge changes very often. A lot of what we do is very incremental. And so it runs into this problem of understanding and controlling that variability so that you can detect the changes that are practically important to you. And I have to shout out to Bill. He sent me a couple of articles that talks about statistical significance and this issue around sample size, that even if there really is a change that for all intent and purposes, you would adopt and go use that vendor or change that process. But because you have a small sample size and it's more difficult to actually detect that difference is really statistically significant. And vice versa. If you have lots and lots of samples, you can detect statistically significant differences even when they don't matter. So you got to be conscious of the sample size. And fortunately, there are better ways, I think. And I think, Bill, when I got your message a while back about some of the issues with the p-values, I'm going to quit trying to say that word, that I tended to like it and use intervals, confidence intervals or confidence bounds and tolerance intervals and prediction intervals as appropriate. At least I hope so. I was using them appropriately. Gave me a graphical. It was easier to explain to other people. It was easier to describe it, and you had a visual. You could see it. And so I tended to enjoy those a whole lot of times. So I'm going to come back to measurement error again, because I do think it's critically important, not just for hypothesis testing, but for pretty much anything we do with measurements. Please check it. Let me leave it as that. Please check it. It's the easiest, quickest way for you to end up with faulty conclusions from what you think is a really wonderful experiment. So make sure that your measurements aren't unduly influencing your conclusions. The other one I see, and I mentioned this earlier, is, oh, this hypothesis testing is cool. Let me compare these 3 different vendors and do, as I described, A to B and so on. The issue is that the ability to detect, if I did enough different vendors, even one, and they were all unknown to me, identical in their performance for what we're trying to do. If I grabbed a sample from each of them and did these A/B comparisons over and over again, eventually one of them would signal that it's true. Kind of it would do the RAM samples and so on. If I make enough samples like this, I could find a difference even though it doesn't exist. Well, other tools tend to take that into account and are designed to deal with multiple comparisons. Hypothesis test not really good at that. And so it's something to be cautious of. Is if you want to compare 3 vendors, well, then hypothesis tests shouldn't be on the table. It shouldn't be something you do. Let's see. I think I forgot to jump over into my chart of all this deals. So let me finish this line of thought here, and then I'll go show that one real quick, and then we'll come back. So one of the things I got, and this is from Bill Meeker, and he highlighted a couple of articles, and there's him and a couple of co-authors, Jerry Han and Nisip, Duggan. And no, I'm not going to get that right. It's about like my name. Nisip and Bill and Jerry have been really in promoting using now I'm drawing a blank. I'm looking right at the word too. Statistical intervals, intervals or confidence intervals around what you're trying to compare. And if I take a sample and I have a confidence interval around that mean and I have a specification, well, if I design it to say that the interval is plus or minus, or it's the 95th percentiles around my estimate, I can tell visually pretty quick, is my specification inside that group or not? And if I really pay attention, I can get a kind of a sense of, well, how close are we or not are we? Is it right on the edge? Is it within or not? What's the criteria? And the p-value gives you some of that, yet it's so sensitive to sample size. Now, part of it is still the confidence intervals still use that variance term. So small samples will still give you an outsized set of confidence. Yet I think what the point is that it's a whole lot less impactful to making a conclusion. And it's focused on, do we compare everything to a p-value of 0.05 and it's yes or no? Well, not really. I remember asking about early on in my learning about statistics is, well, what is this criteria? Where did this come from? Why do we say it's got to be at the 95 percentile or less before we believe it's really different? Or something like that, way out in the tails. Where did that come from? And as far as I can tell, it's pretty arbitrary, and we pick nice round numbers. The setting a p-value of 0.05 is not a whole lot different than setting it at 0.049, yet we pick 5, or we pick 0.1, or we pick 0.2 or 20%. Those kinds of of round numbers we tend to use. And I've even seen in medical devices for critical to patient safety, they'll use a very high or a very small p-value, 0.01, for example, requiring lots and lots of samples and lots of more work to make it happen. Or if it's cosmetic or stuff, they'll use a very different p-value. Yet the issue is that the it's not always a hard and fast rule. And this idea of having something that's practically important, what change matters to you? What difference are you actually looking for that would say, yes, the added expense of this new process to make these bike frames is worth that 200-gram difference in the final result. And so we're always making these comparisons with other variables that aren't in the statistics. Do we have a stable supply chain? Is their process stable? Is the cost benefits there or not? Is it worth the extra amount of effort or time or whatever resources we have to make this change? Those all play a role in making the decision. And so the amount of change that is important for the process, for our customer, and so on, is outside the statistics piece of it. And so we bring it in by looking at, say, a graphic of these two histograms and knowing that the scrap rate's going to go up slightly because we're going to not always meet that new target. Yet we can see from the histograms that it's going to be a very small amount of scrap. Yet it was enough of an overlap that we couldn't, from a hypothesis point of view, say that they were different. But practically, we can see that they're different. And so I like the idea of plotting it. And intervals is one way to do that, adds a little more finesse to it. Yet simply plotting it and putting confidence intervals on it is a great way to help include the practical differences that you really are trading off with all these other variables when we try to make a decision on a process improvement, for example. Let's see. So let me jump out of this. Before I forget, I'm going to go to an article I wrote, years ago. It's on the Ashendo reliability. It's called Hypothesis Test Selection Flowchart. And it's an amalgam of a bunch of other information I've gathered about control charts. Let me open this up a little bit bigger. And then sorry for the eye chart on all the formulas, but you can find this. It's select a hypothesis, or selecting hypothesis test is the page for it. And it's basically what kind of data do you have? Is it attribute data or continuous data? Is it paired or not paired? There's all kinds of variables here, and even down to what kind of distributions you're dealing with. And are you interested in the mean, or are you interested in the variance? And even whether you know the mean and the variance, for example, of the one you're comparing to, the variance of the one you're comparing to. And some of these formulas are kind of crazy looking. I think that near the bottom of the screen here, there's a degrees of freedom one yeah, was very happy that spreadsheets became available when I started to use that one. But the idea is, and I know that this isn't even complete. There's a whole slew of non-parametric techniques that are used to make comparisons, and those aren't on here. And there's probably even more types of hypothesis tests available so that you could probably add to this. So if anybody knows of other styles of tests that are salient and useful, let me know. We can update this thing and make the fonts of our formulas even smaller, the math parts of it. All right. Let me see if I can find my slide deck again. Oh, I forgot something. So let me get out of here. Go back to this page here. Let me give you the link to it. That's what I really wanted to do. All right, so now I can go back to my presentation right here, and I'll paste the link in the chat. There you go. Sorry about that. we make comparisons all the time, using contour plots, using confidence intervals, using design of experiments, using analysis of variance, ANOVA, I think that's what it stands for. And there are non-parametric methods I mentioned a few times. There's a whole list of those. Is matching the tool that you're using to help you make the comparisons is a good first step in trying to then make an important decision. The basic process is collect good data, set up a good experiment, make sure your samples are coming from as best you possibly can from a random sample of the population you're dealing with that you want to make a judgment about. Pay attention to the details like measurement and measurement error and so on. The idea is that we use these tools, hypothesis tests and others, to inform decisions, and sometimes very, very important decisions. So one last story. Years ago, I got called up to a division when I was working at Hewlett Packard. I got called to a division, had to get on a plane. I went and talked to the person that was invited me up, and they said, "We want you to go talk to the finance team." He says, "You had to fly me all the way up here just so I could go talk to your finance guy?" And he goes, "Yeah, we don't seem to talk the same language." And I said, "Well, what are you trying to tell them?" He says, "Well, they wanted to know what the expected failure rate was for the new product we're making." And we gave them a Weibull plot. And the Weibull plot was very well done. It included all kinds of cool stuff in it. They considered this, that, and the other thing. They had some really good evidence behind it and good data set and all the stuff they did very, very well. And he said, "But they don't seem to understand it." Okay. So I got introduced. I sat down with this guy and he had this spreadsheet that I didn't know they could do stuff like that. It was amazing. It factored in production volume, scrap rates, all kinds of information was going into this. And at last I asked, "Why am I here? Why do you need somebody to help you understand this plot?" And he said, "Well, this is $1 billion decision. We're getting ready to inform the board of directors whether or not they should create a new factory or not for our product. And the failure rate's important. Do we make enough of them to serve warranty and all this other stuff? And so we need a good estimate of it." I says, "Well, you got a really good estimate of it right here." And he went, "I don't know what this means. It's a plot. It has these numbers on the side and a funky scale and it has a straight line on it. And what do I do with this?" So I showed him the formula for the Weibull cumulative distribution function and said, if you're interested in the first month, here's the failure rate times what you think the production's going to be. That's how many units you're going to be lost for failures for one reason or another, and so on. And the light bulb went off for him and goes, "Oh, well, this is cool. Well, what were you using before?" He says, "Well, I just took the middle of it. It looked like 50%. So I pulled that number off and used that estimate in my calculator here, in my spreadsheet." And well, what would the recommendation be? This is, "Well, you need to build this new factory because we need to support the production and the expected failure rate." I said, okay, well, that expected failure rate, if half of them failing, doesn't occur until about 10 years after the warranty expires. So you might want to adjust that for the one that you really need to pay attention to. And he very quickly was able to take that formula and add it to the system, his process. And instead of a single point estimate, he was able to put the curve in there. And they were able to then simulate what's the failures in 1 month versus and its effect on resale and so on like that. They had all kinds of marketing information about how the product worked versus its failure rate. And the result was we don't need to build a new factory. Now, of course, there was lots of other factors involved, but a pivotal piece of it was what's the failure rate estimate. And so if I'm doing an experiment and I wanted to know if our new product is a lower failure or not, well, how is it going to be used? How well do I need to actually understand, is this difference real or not? And doing a hypothesis test may be quick and easy, yet is it sufficient to inform $1 billion decision? So part of the process of using any of these methods and making comparisons is to what extent, to what's important. Why is it important? And to what extent is it important? How much effort and precision do I need to have to detect whether there's truly a difference or not? And is it really important from a practical point of view? So the idea of making comparisons is part and parcel to a lot of what we do. It's either improving products or processes, and it's all great. Yet understanding some of the nuances or ways to really get the most out of these methods and what alternate methods may be more appropriate uh, is part and parcel of what we should be doing all the time anyway. All right. So it looks like I got about a minute or two left before the official time ends up. And at some point here, I thought I had a link to, let me see if I can find it. Here it is. Oh, will it let me copy it? No. So in 2017, NISIP, Jerry and Bill's wrote an article for the Quality Progress magazine. It's Fallacies of Statistical Inference, the Case for Focusing Your Data and Analysis Beyond Significance Tests. And it was in Quality Progress, issue 50, or well, I don't know what the numbers are, 51 parentheses 11 comma pages 56 to 62. And so hopefully you can find a copy of that. Let me know if you want the full reference for it. I can email that to you. I was hoping I could cut and paste it out of the notes in this, but apparently not. And there's a handful of other ones. I think Jerry Hahn's been after this, is from what I understand, from the 70s, highlighting this difference, and has an article that I'm still trying to track down. I got a lead on it, but I don't have it yet, out of some journal back in the 70s. So it's been a known problem for a while. We've got alternatives, including statistical intervals, and is a way to make these comparisons a bit less sensitive to your sample size, but also easier, I think, easier to explain to somebody else, especially when you're looking for information that you can use in concert with all the other variables that we have to deal with in making decisions. So I think that's it. Let me see if there's any other questions or comments. Got a couple of thank yous. I think we're okay. All right. So Nasri is asking, so for multiple vendors, what methods are available at market? I'm not sure what I know what you mean at market. Um, from if you're comparing multiple vendors, I would use analysis of variance as a starting point. I'd also plot it as the start, the very first piece of it. There's lots of different tools, if that's what you mean, different statistical packages and algorithms and textbooks and so on. There's plenty of them out there that can do it. But look for a tool that does multiple comparisons, and it could be a non-parametric method, which I'm not familiar enough with all the variations there. I know I've written about a couple of them at one point or another. But analysis of variance is probably the place I would start at. Yet I would need to know way more information. I don't typically look for, is it Minitab or Weibull++ or R software or whatever package. I tend to look for, well, what's the method that fits the type of data set and type of decision I'm trying to make. And then I go find a way to go do that. So I might use Mathematica or MathCAD, or I might use R with a package or create my own algorithms to, implement algorithms in it, but I always want to make sure that the tool I'm using is good enough in the right tool for what I'm trying to do, as opposed to say, well, I'll use Minitab and use whatever they have to make this multiple comparison. That's what led me into when the only tool I knew was hypothesis testing. And I started comparing multiple vendors only to realize that really wasn't what they're meant to be used for. And was probably going to lead me astray pretty quickly. Oh yeah, Michael, is type 3 error. Yeah, definitely. Yeah, the type 3 error, I love that term. I don't remember where I first heard that, but it was basically you get a perfectly good answer for the completely wrong question. Um, and so you can spend a whole lot of time sorting out the thing that really doesn't matter, nobody's interested in. So yeah, there is the type 3. I think my boss accused me of the type 3 error syndrome at one point or another. Because I would find something fascinating and go explore it. And then he goes, nobody cares. I goes, well, I care because you're not paying the bills. So put me in my place there. All right. You're welcome, Don. Welcome, Nasri. Not sure what I'm talking. As usual, I don't remember what I'm talking about next month. In about 2 weeks, we'll have Chris Jackson back. I think he's talking about exponential distribution and some of the issues with that. And I think he's using that title as a back end to get after the MTBF type stuff or MTTF. Should be interesting. All right, with that, I'll say have a great rest of your Tuesday and enjoy making comparisons out there. Use the appropriate techniques and tools and be aware of the various assumptions involved so that you can be well informed as you make the next set of decisions you need to make. So with that, have a great rest of your day, everybody. Thanks for attending and your comments and questions.